Good evening, everyone. My name is Amit. We have been talking for the last week. We started talking basic electronics course, that is NOC 23E62, taken by Professor Mahesh Patil. We'll be discussing problems related to the lectures that we are being discussed, and the problems which are quite similar, which you will encounter in your assignments. So yes, last week we did one session. Today also we'll do another session with again the topics related to the lectures. We'll wait for a few more minutes, waiting for other people to join, and then we'll start. In the meantime, if you have any queries regarding the last session or any topic in particular which has been discussed in the lectures, you can feel free to ask. But otherwise, we'll wait for a couple more minutes for other people to join. Good evening, everyone. I hope my screen is visible. Can someone please confirm?
It's visible, sir.
Okay, good. So, as I mentioned, this is week two. We are solving problems related to the NPTEL course Basic Electronics taken by Professor Mahesh Patil, ID being NOC 23E62. My name is Amit. I'm a PhD scholar at Indian Institute of Science, Bengaluru. And we'll be talking about, we'll jump into the session. Before starting, let me summarize what we had discussed in the last class, which was corresponding to the week one of the curriculum for this course. So we had talked about uh, um, how to get a Thevenin equivalent of a circuit. Similarly, how to get a Norton equivalent. So if you remember, any random circuit can effectively be uh, reduced to this form: VTH RTH, where and we are looking at through these nodes A and B. This is the Thevenin equivalent. Correspondingly, you can also get a Norton equivalent, which is IN, and this is the RN, where RN was equal to RTH, and we also saw that. So RN was RTH and VTH is IN times RTH. So these we changed. You can play with them based on your requirement, which one suits you better. And finally, we also solved a few problems using nodal analysis. That is assigning so any for any random circuit, we using KVL and KCL essentially. We provide node voltages to the relevant nodes. We also used a reference voltage, which was usually ground, and then and then we also saw a superposition theorem, where if we have multiple sources, multiple independent current and voltage sources, you can deactivate them one by one, and then correspondingly obtain the requisite current or voltage in whichever branch you want, and then you can simply algebraically add up using of the contribution of the other sources. It was a straightforward thing. And by deactivation, so the key thing here was deactivation, and by deactivation of current source, means you open circuit it. Mind you, deactivation of independent sources only, of independent. Similarly, for a voltage source, for how do you deactivate an independent voltage source? Short it. So these were the considerations that we took, and finally we had a brief look at the phasors. Phasors are nothing but a way to represent the sinusoidally steady state of any voltage or current or any other values that we encountered. And we also saw that these we while representing them or while doing their analysis, we represented them as a complex number, so they were usually in the form of, as typically a complex number is a plus iota b, or we also saw that they were also in this form, r delta theta, but phasors is typically represented at xm delta. So this is the form that we had seen in the last session. So this was from the last session. I'll pause a bit over here. If you have any conceptual difficulty in some specific aspect, please feel free to ask, because when we go forward today, we are going to be assuming that you are comfortable with Thevenin equivalent and Norton equivalent, and as well as nodal analysis. So so if you have encountered any problems, then you may ask, otherwise we'll move forward. So I'll wait for a minute or two here and for your responses. All right, so if there are no concerns regarding the last session, we'll now jump ahead and start with today's session. Okay, so this is the first question. Again, this question is very closely related to what you would have seen in your lectures. Okay, so just give me a second. Right, so this is the first problem, and what we are required here in the circuit shown in the figure, the capacitor voltage VC at t equal to 0 minus is 0 volts. What is the time constant of the circuit? So this is the circuit that is given to us. This is an independent voltage source, which is a step function. There are two resistors and a capacitor, and for the first part of this problem, we are required to find the time constant of the given circuit. So how do we go ahead doing that? Now till now, what we had only talked about when we talked about Thevenin and Norton equivalence, it was a straightforward problem in the sense that the time dependence of voltage source or any independent source was not there. It was 5. If it was 5 volts, it was 5 volts throughout. If it was 3 volts, 3 volts throughout. Similarly for independent current sources, but here we have a step function. So clearly, what we'll try to do is we'll try to break the problem in two parts. Why? Because we can see that the jump is happening at t equal to 0 volts. So in this problem, as if we'll have two universes. One for yes, this is a time variant problem. So here, because we are required to analyze the ultimately we'll try to find out what is the capacitor voltage with respect to time. So these are called transients. Transient means anything which is varying with respect to time. But that's among the later parts. So for starters, we are just required to find the time constant for this circuit, right? So how do we do that? So it's straightforward. If we just give me a second. Alright, so now we are required to find the time constant for this circuit. Now how do we do that? So we treat it, so please note that at time t greater than 0, this is the time that we are interested in. This is time t greater than 0, this is time t less than 0. So we're not interested in time t less than 0. However, we can also draw a circuit. But for the sake of completion, what I'll do, I'll try to break this problem in two parts. So I'll now draw the circuit for t less than 0. How does the circuit look like? So the circuit will look something like this. Vs is 0 volts for t less than 0. This is R1, this is R2, and this is our capacitor C, right? This is for t less than 0. Okay, so let's say if I want to find the time constant of the circuit. So we have seen that if you have gone through the lectures, you must have observed that the time constant tau is given by R Thevenin times C. So whatever the Thevenin resistance of this circuit times C will be the time constant. So this means we need to find the Thevenin equivalent across this capacitor. So for this circuit, so this is fairly straightforward. If I can now drop this 0 volts, so this will look like R1 parallel R2, and this is where our capacitor is, right? So this is where our capacitor is. So RTH will simply come out to be R1 parallel R2. This is 3 parallel 5, 3k parallel 5k. So this will come out to be 3 times 5 divided by 8k. So this will come out to be 15 by 8k. So this is the R Thevenin for t less than 0. Let's draw the circuit for t greater than 0 now. So for t greater than 0, Vs is 5 volts. So I'll draw this as 5 volts. This will be R1. This will remain R2. And this is the capacitor that again we are required to find the Thevenin equivalent as if we look from the capacitor side. So for finding Thevenin resistance, we short circuit all the independent voltage sources. So we'll simply replace it by a wire. So this will be R1, this is R2, and again this is the capacitor that we have over here C, and we are required to Thevenin resistance across this. So again R Thevenin will come out to be R1 parallel R2. This will again come out to be 15 by 8k. So what you have noticed is that since the topology of the circuit remains the same, even though a step comes, the Thevenin resistance of the circuit does not change, and thus accordingly, so if I calculate the time constant will be R Thevenin times C. So this will come out to be 15 by 8k times the value of C is 4 microfarad. So this will come out to be 15 by 2 k times micro. This will be milliseconds. So this will come out to be 7.5 milliseconds. So let's see, do we have an option? Yeah, we have an option, and this is also happens to be the correct answer. So D is the correct option, 7.5 milliseconds. How did we arrive there? I'll repeat. We just drew the circuit. We just found out the Thevenin equivalent of the circuit, and since we are interested in t greater than 0, that's why although I derived for both the cases, for t less than 0, greater than 0, we are interested in t greater than 0 because that's where the transient will lie, and we found out the time constant that we arrived at is 7.5 milliseconds. So I'll pause here for a bit. If you have any comments about this, any questions, please feel free to ask. Just give me a minute. There are some for all square input. Yes, for this topology it comes out to be. Why I'm saying this topology? Because we'll see some further questions in today's session where that might not be the case. If the circuit changes, if the circuit form changes, this means the components like current sources, voltage sources, they're different for different times. Then naturally the Thevenin and the Thevenin resistance will change for the circuit because the circuit itself has changed. So we'll see that in the following in today's session, in the following questions. Right. So now let's move forward. Right. So now we'll move to the second problem. So second problem naturally builds up on the first problem, just like we saw in the last session. So all these problems are sets, right? They are not independent of each other. So let's have a look at the second problem now. Second problem says in the circuit of Q1, this is the circuit by the way, what is IC 0 plus? So we are required to find the IC, that is the current through the capacitor. I should have made this clear. So 0 plus means just at the time, just right of t equal to 0. So the step is at t equal to 0. So we are interested in finding in the current at, let's say it's at a time like this, just right of it. So this is t equal to 0 plus. This however would be t equal to 0 minus. right? So this is the nomenclature that we are following. So just you have to be mindful of that, because the values will not be, will necessarily not be the same. So for instance, if I say Vs 0 minus, that means the value of Vs at 0 minus is, you can clearly say it's 0 volts, right? However, Vs at 0 plus, that means just after time t equal to 0, it is 5 volts. This is the characteristic of a step function though, and that's what we are seeing here. Right, so we are required to find the IC at time t equal to 0 plus. So let's go ahead and do that. So we are here, so we're required to find IC at 0 plus. What is this value? And this is the circuit that we have. Okay, so we are required to find that now. Excuse me. So just before going into this, a quick recap of how a capacitor behaves. So this is the how should I say, this is the commanding expression for a capacitor. So where Q is the charge stored by the capacitor, C is the capacitance of the capacitor, and V is the voltage across the capacitor. So this is the expression which we'll use to for our KVL, KCL, for everything. This is the expression that will be used. The corresponding expression for a resistor. Can somebody tell me what is the corresponding expression for a resistor? This is for a capacitor. What is the expression for a resistor?
Equal to IR.
Yeah, V equal to IR, which we typically know as the Ohm's law. Third component is inductor. What is the expression for an inductor?
L di by dt.
Okay, so I'm trying to ठीक है, fine. We cannot avoid that in this case, because you see that it will be okay. We'll come to the inductor later, but let's, for the time being, let's just stick to Q equal to CV. And by the way, these are the expressions that for others that we'll see. Inductor we'll see a bit later, so because it has a differential term already in the I'll not go into this. So yeah, let's stick to this, right? So we are required to find IC at 0 plus. So what I'll do, I'll take a derivative on both sides. So this will come out to be dq over dt equal to, C is a constant, C will step out, C dv over dt, and dq by dt is nothing but the current. So I equal to C dv over dt. This is the expression for a current flowing through the capacitor. So this is nothing but IC equal to C dv over dt, right? So now this is the thing that we'll use over here. Okay. So now if you carefully see, there is one more concept that that we should talk about before we try to solve these problems. VC across capacitor can't change abruptly. Now this is a term that I'm using, abruptly. Abruptly means, by that I mean dv by dt should be close to 0. This means voltages should be very smooth in changing. It cannot be very high change. Why? If dv by dt is high, IC will be very high. If IC is very high, this means it can draw huge amount of current from this voltage source, and KVL will be violated. Professor Patil has discussed this in detail in the lectures. If you are interested, you can go through that. So, but this is the important thing, that VC across capacitor can't change abruptly. What this would mean is that VC at 0 minus should be equal to VC at 0 plus, because this is the time at which some change is happening. So whatever the voltage is at 0 minus over here, same voltage will be at 0 plus. So what is the voltage at 0 minus? So in the problem we were given that VC 0 minus was 0. Okay, so VC 0 plus again will be equal to 0. So that was given to us. And now if you try to either you can apply how should I say, either you can apply KVL or you can use Thevenin equivalent, whichever method we choose. So now for the second step, what we'll do is we'll write the expression for VC at 0 plus, mind you. So this will be equal to so this is the general form. This is the general form for the expression of VC for these types of circuits, because in this case, by these types of circuits I mean only the resistors and maybe a voltage source. So it means, so, and we know that. So now what we'll try to do, we'll try to find out just the values of A and B. And by the way, tau is the time constant that we already know, so we need not worry about that, right? So this is the VC for time dependent for t greater than, so I should say VC at t and where t is greater than 0. So this is how I should define it, right? So we know that at time t equal to 0, at 0 plus VC is 0, because capacitor voltage can't change. So if I put t equal to 0 in this expression, this will come out to be A plus B. This will give me B equal to minus A, and this expression will come B is minus A. So there are different forms of saying it. Some people express in terms of B or in A. It doesn't matter, however way, whichever way you want to express it, right? So, oh no, sorry, I made a mistake. VC at 0 minus was not 0, so we have to calculate VC at 0 minus, that is at just before just give me a second. VC at 0 minus is 0, sorry, so it was 0, so this was 0. Yeah, so this was the expression. Now what we are required to do is that, now what we still constant remains. So what we'll do is at step 3, at t tends to infinity, what happens? T tends to infinity, circuit will stabilize, it will achieve a steady state. So let me draw that circuit now. Okay, so this will be 5 volts, right? And we saw that this is 3k, this is 5k, right? This is like this. And at steady state, no current will be drawn, capacitor will be fully charged, sorry. So, and a capacitor will draw no current, it will be open circuited. So this will be an open circuit, so no current can flow over here, right? So all the current that's whatever is the current that is flowing, it will be flowing only through this loop, right? So what we can do, so we can see that VC, this is the VC voltage here, VC at t equal to infinity. So VC at t equal to infinity will be nothing but voltage across 5k resistor, voltage across 5k, and this we can evaluate simply by using this is a potential divider. So I can say 5 divided by 3 plus 5, that is 5 volts, divided by 3k plus 5k into 5k. So this will be 25 upon 8, 25 upon 8 volts. So VC at t equal to infinity will be this. So I'll take all of these values over to the next slide. So this is VC t, this is coming out to be A e to the power t by tau minus 1, and we saw that that VC at t tends to infinity points to 25 by 8 volts. So I'll simply put t equal to infinity in this expression. So if I put 25 by 8 equal to A, there is a minus here, yeah. So minus infinity by tau minus 1, tau is a finite quantity, so this term will vanish. This will give me A equal to minus 25 over 8. So we'll get VCT equal to 25 by 8, 1 minus e to the power minus t over tau. Now we have just gotten VC. What we required was IC. So how do we get IC? We just saw that IC is nothing but C dV over dt. So this will be C 25 by 8. If you differentiate this, this will come out to be 1 by tau e to the power minus t by tau. It will be minus 1 by tau will come, the minus and minus will get cancelled. So I'll try to plug in all the values. So 4 microfarad times 25 over 8 times 1 by tau, what was the time constant, 7.5 milliseconds, times e to the power minus t over tau. So this will come out to be 225 times 7.5 . Yeah, we are interested in finding the current at just 0 plus. So I'll put IC at 0 plus. So this term will vanish. So this will come out to be 25 times 7.5 by 2 times 10 to the power minus 9. Oh, there must just give me a second. Oh, sorry, tau was in denominator. This was 7.5 milli. So I'll write this here. IC at 0 plus would be 25 by 2 into 1 over 7.5. So there's a micro, this is milli, so only milli will remain, milliamps. So let me get my calculator. So this will be, yeah, so answer is coming out to be 1.67 milliamps. So is that an option? 1 point, yeah, so 1.67 is the answer over here. Right. So in this problem, what we had done was that we are required to find the current after the step. So, and we utilize the principle that voltage cannot change suddenly across the capacitor, and then we derive the expression for the voltage transient for this capacitor, and we simply differentiated it when time t greater than 0 to arrive at the current, which was the expression, which was the value that over here. And since that we put t equal to 0 to arrive the value at the time t equal to 0. So that's what happened over here. Any comments, any doubts, please speak up. So give me a second. Yeah, any doubts, any comments? Am I going too fast? Differentiation is wrong. Okay, can you tell me, please, make me understand what step I did wrong? Because if you differentiate e raised to the power minus t over tau, e to the power ax, the differentiation is a into e to the power ax. So the value of a is minus 1 by tau, so it comes out, minus minus gets cancelled. So I think I did this correctly. Anaga, I think I did this correctly. Okay, right, so we found out the current at time t equal to 0. Now the next part of the question says, in the circuit of q1, what is vc infinity, right? So now the problem becomes much simpler, because if you recall, I have already derived the expression for vc. Where was it? Yeah, vc was here. So vc we derived at vct 25 over 8 1 minus t by tau. So I'll write this here. So we saw that vct was 25 by 8 minus t over tau. So at vc equal to infinity, we also saw how to get vc at infinity. The concept here involved is that at time t equal to infinity, capacitor will no more be charging, right? Because it at infinite amount of time, it would have been already charged. This means this would become open circuited, right? That's how we derived. If this becomes open circuit, so if this becomes open circuit, then the circuit diagram will look something like this: 5 volts, 3k, 5k, and this is the vc over here at infinity. At infinity, this will become open circuited. So now you can simply see the current will flow only this loop in this way, and that's how we got that the vc infinity, that is the voltage across this resistor, was coming out to be, excuse me, yeah, voltage across this resistor, we saw that was coming out to be 5 volts divided by 3k plus 5k times 5k. This is 25 over 8 volts. This is this, and that was the coefficient that we saw, that was over here. So 25 by 8 should be 3 point something, 3.125. yeah. So this is the option B. We had already, I mean, it's just that I did it again just for the sake of completion, but we have derived this 25 by 8 expression earlier also. Okay, so now we have 25 by 8. We now have the complete expression for vc effectively, right? Now the questions asked, in the circuit of q1, what is I1 at t equal to 15 milliseconds? Okay, so this means we must evaluate the I1 as a function of time. Please note that we know IC as a function of time, right? right? How do we get I1 as a function of time? So this is slightly different. We have obtained IC, but we want to find I1. So let me do it over here. So we want to find I1 as a function of time, and then we'll simply put t equal to 15 millisecond. Actually, there are two ways of doing it. So there is a first approach. So approach one can be, you find IC at t equal to 15 and then do a nodal analysis. And approach 2 would be, you obtain I1 as a function of time itself. So we can do it either way, but using this we'll simply use the KCL. So what I'll do, first I'll try to solve it using approach 2, and let's see if which one is better. So approach 2 I'm taking now. Approach 2. So we'll find I1 as a function of time. So let me apply. So if you apply KCL over here, at this junction, right, this is approach 2. So KCL, it says incoming current should be equal to outgoing current. So incoming current here is I1. This should be equal to outgoing current, which is I2 plus I3, right? Okay. And by the way, just be mindful that all of them are time dependent. We are operating only for t greater than 0. This is the assumption that's here, right? So I2 will be nothing. If I apply Ohm's law across this resistor, this will be VC over R2, and this I3 is nothing but IC, right? Yeah. So now, and mind you, these are all time dependent functions. These are not constants. So I can now simply write it as I1 of t should be equal to VC of t over R2 plus IC. And we know the expressions for VC of t. Sorry, this is IC of t. VC of t was, if I remember, 25 by 8. So R2 will come here, and it was 1 minus e to the power minus t by tau plus the expression for IC, we had derived that somewhere. Yeah, it was this 1.67 milliamps, and then e to the power minus t by tau. So 1.67 milli e to the power minus t by tau. So this is the complete expression, and now we'll simply put t equal to 15 milliseconds, right? So now we put t equal to 15 milliseconds, and mind you, tau is 7.5 milliseconds, right? So effectively t by tau will come out to be 2. T by tau will come out to be 2. And let me just put these values over here. So R2 is 5, right? So R2 is 5. So if I put 5 over 5 by 8, this is 0.625 milli. 1 minus e to the power minus 2, t by tau is 2, plus 1.67 milli e to the power minus 2. So what will happen? So 0.625 plus 1.67 is 2.295 milli, and sorry, it won't happen, because it will be 0.625 milli plus, if I take e to the power minus 2 common, it will be 1.67 milli minus 0.625. So that's what it will come. So it's only 0.625 milli plus what's 1 over e square. 1 over e square is 0.13 times, that is 1.67 minus 0.625. So this will come out to be 0.1414. So this whole term is coming out to be 0.1414 milli, and if we add 0.625 milli to this is coming out to be 0.767 milliamps, right? So do we have any such option? Yes, there is an option. This is option D, 0.77 milliamps. Just excuse me. Yeah. So so we were required to find I1 at t equal to 15 milliseconds, and we had done that. Just to summarize how we did that was, we used the second approach, that is we applied the KCL at this node, and we already know the expression of VC and IC. I wrote their expressions, and since t equal to 15 milliseconds, that's the point at which we are interested to find, and we simply found out that I1 at t equal to 15 was this much. So yeah, that's that. So t by tau equal to 2. We found 0.767 milliamps, and that is the option D, that is over here. So that's all. Okay, so that completes the first set of questions. I'll just briefly go through what we had talked about for this set. So first we saw that we noticed that this is a step function, right? Second thing we found out the RTH for both the regimes being t less than 0 and t greater than 0. These regimes will be defined where the step lies. So in this question the step lies at t equal to 0, and we found that the RTH was same for both. It might be different for different circuits, which we'll see in the maybe in the next question. Thirdly, we noticed that VC at 0 plus should be equal to VC at 0 minus, because voltage can't change abruptly. Fourthly, using this expression and the fact that originally VC 0 minus was given to us at 0 volts, and VC at infinity, which we can derive using the KVL, which was 25 by 8. This we arrived at using KVL, right? We could, using this information, we could populate that VC for t, which is a e to the power minus t by tau plus b, this format. We found the value of a and b, and once we know VC, then we can get IC as C dVC over dt. Using all this, and then once you know V and I, and then you can evaluate I1, I2, and everything, and every node voltage and every branch current can be identified. And these are the steps that we have followed, which we have enumerated over here: 1, 2, 3, 4, and 5. So I'll stop here for a minute or two. If you need me to repeat some particular concept or some particular stage of the problem, please speak up. Approach 1. Okay, just give me a second, I'll do that. Just give me a minute. Okay, so you want approach 1. Okay, let me make some space. Found it. Okay, right, I hope my screen is visible, right? Yes, please respond if my screen is visible, because I am not able to okay, yeah, right. So approach 1. So what was approach 1? Approach 1, I said we first find IC at t equal to 15. So again, the main part remains the same. We again will have to use KCL only. Sorry, this time for approach 1 we can use by solving KVL. So how do we do that? So you see, we are required to find I1 at t equal to 15. So if you carefully see, if I apply Ohm's law across this resistor, right? So I1 times R1 should be equal to Vs minus Vc. Vs, and this node is nothing but Vc. So I get the expression Vs minus Vc over R1, right? Vs I know at t equal to 15, and Vc I need to calculate at t equal to 15. T equal to 15 milliseconds, by the way, over R1. So units is milliseconds, right? So Vc at t equal to 15, we know it's 5 volts. You can see it over here. Minus, we just need to find Vc at t equal to 15 milliseconds and divided by R1. So how do we find Vc at t equal to 15? we can simply say t equal to 15 milliseconds, that is, so that we know 25 by 8 1 minus e to the power minus t by tau. So this will be 25 by 8 e to the power minus 2. We saw this value, t equal to 15 milliseconds, tau is 7.5. So this will come out to be, let me calculate. So 1 over e square is 0.135 into 25 by 8. So this is coming out to be 0.423 volts. Put this here, 5 minus 0.423, the value of R1 is 3K. So you will get 5 minus 0.423 divided by 3K. So just give me a second. There's a calculation mistake. So this is actually, this is not this, this is 2.7. So if I click this over here, so this is 5 minus 2.7 over 3K. So 5 minus 2.7 is 3.3, sorry, 2.3 over 3K. And if you calculate this, is 2.3 over 3 is nothing but 0.767. K is denominator, so it will come in milliamps. So this is the first approach that I have, where I listed it somewhere. Yeah, using nodal analysis. So that's what we are doing here. So just apply Ohm's law across this. We know the node voltage for this, and we can simply found it out. And again, obviously the answer comes out to be the same as 0.77 milliamps. Yeah, okay, so now we'll quickly jump to the next set of problems. This is slightly different, so again I'll try to enlist all the steps that we are trying to follow over here, right? So the question says switch in the figure has been open for a long time. So these are the terms that you will this is an important phrase here, for a long time, and closes at t equal to 0. What is the time constant of circuit for t greater than 0? So what do we mean by that, for a long time? When this phrase is used, for a long time, what what we typically mean by this is that this means all the capacitors can be assumed, if they are functional for a long time, to be open circuited. Capacitors to be open circuited and inductors to be short circuited. Whenever this phrase essentially means this electrically, this phrase from English will electrically mean that capacitor can be assumed to be the open circuit and inductor can be assumed to be at the short circuit. Okay, so now we'll try to use the same approach over here. The first problem asks what is the time constant for this circuit at t greater than 0. So this is the circuit that we know. Again, reproduce this over here. So if you want to find the time constant for t greater than 0, mind you, so for t greater than 0, this means this would be closed, right? So let me draw the circuit. So this will look something like this: 10 volts, 2K, 3K, 5 microfarad, and then again 2K. So this is how the circuit will look like. And for t equal to, and if so effectively, if we find the so if we find the Thevenin equivalent for this circuit, right, that will simply solve our problem. So let's do that. So to find the Thevenin equivalent, that means we more interested in finding the RTH. So we simply short the independent voltage source, deactivate that, so it will become 2K, 3K. This is the nodes across which we want to find the Thevenin equivalent across the capacitance, and here we have one more 2K, right? So if you clearly see that 2K, 1K are in parallel, right? So I'll draw this like this now. 2K, this is R1, 3K, this is R2, and then this is again 2K, this is R3, and here we have our capacitor denoted by A and B. So I'm calling this A, calling this B accordingly. So now we can clearly see RTH would be R1 parallel R2 parallel R3. This will be 2K 2k, parallel 3k, parallel 2k. So 2k parallel 2k will become 1k, 1k parallel 3k. This will be 3 minus 1 over 3 plus 1 k. This will be 3 by 4k. So this will come out to be 0.75 kilo ohms, and we know time constant is nothing but RTH times C. So the value of 0.75 times C is 5. K into micro will become milli, units will be seconds. So 0.75 into 5, this will be 3.75 milliseconds. Do we have an option? Yeah, we have an option C, 3.75 milliseconds. So nothing changed in this circuit. However, as I told you last time, the RTH before and after will be different, right? For RTH t less than 0, if I try to find the equivalent for this, right? So kindly note that t less than 0, this part of the circuit does not even come into the picture. Only this part comes into the picture, right? So this is the key difference. So here the circuit itself has changed. So time constant before the event is happening in this case also at t equal to 0. The RTH might not be the same every time, because circuit itself might change. The topology of circuit might itself change. So this is yeah, so we found that. Excuse me. Now the next part it asks is, what is VC infinity, right? So we are again required to find that. Now this time we are going at to the positive infinity side. Now again the same, again we'll assume the same thing, that at time t equal to infinity the capacitor has charged. So capacitor will not draw any current, right? So what I'll do is that I will draw this equivalent circuit at t equal to, when t tends to infinity. So how will the circuit look like? So voltage source R1, R2, they will remain the same. T equal to 0, this has been closed, so this will remain closed, and so this has become open circuited, right? No current will flow here, and this will become R3, right? So now we are required to finding this voltage VC, right? So yeah, kindly note that. So I'll redraw this circuit. 10 volts, R1, R2, R3. Did nothing but just brought R3 this side, and this is nothing but your VC, right? So now you can see R2 and R3 are in parallel. 10 volts, R1, R2, parallel R3, and this is nothing but VC. This is purely a potential divider, so I can simply say VC should be equal to the voltage source 10 volts divided by the total resistance, which is R1 plus R2 parallel R3, times R2 parallel R3, right? So this will be 10 volts. Let's evaluate R2 parallel R3. So this will be 3k times 2k over 3k plus 2k, so that's 5k. So 6 by 5, that's 1.2k. Okay, so this is 1.2k divided by R1 is 2k, so 2k plus 1.2k. So this will be 12 by 3.2. K and k will get cancelled. So 12 by 3.2 will come out to be 3.75 volts. Is that an option? Yes, that is an option. B. Just to reiterate what we had done in this problem, again we did the same thing, that for time t equal to infinity we'll assume that this capacitor has charged. Now the key thing, there's one assumption that I'm making here. So there's one assumption, and that is no oscillation, right? You might encounter, especially when they're LNC, right? Those circuits are oscillating. We'll encounter them sometime later, but I'm just pointing it out over here right now. that this assumption that we are quite boldly that are assuming that capacitor will get fully charged and it will and thus it will behave like an open circuit, right? This is so there's one assumption that's involved over here, that there's no oscillations, right? And there are a couple of other assumptions that we have been making, which I'll list at the very last. Those are some known idealities, but for now we'll just go ahead and move forward. I'll again pause a moment over here. If you have any doubts or comments, please speak up. I'll also look at the chat. Okay, so if no doubts, then we'll go ahead and solve the next part of this problem. So problem 7. Again the same circuit. It asks that what is Vc at t equal to 8 milliseconds, right? So if I remember, we had calculated tau, that was 3.75 milliseconds, I think, right? So now the required time is t equal to 8 milliseconds, and it says we are required to find the value of Vc. So essentially where tau is 3.75 milliseconds, that has already been given to us. Okay, so right, so since we are required to find Vc as a function of time, and if you recall before, it can be written as in this form. This is the most general form for an RC circuit with you can say with the other sources being independent. So you can just take this expression, and so what we required here is that there are two constants, right? So we need two boundary conditions. So we have two boundary conditions. Vc, we know that Vc at just 0 plus, I think that was, we calculated it right somewhere. I think so. It's okay, we can calculate it right now. So Vc at 0 plus we need to find out, and Vc at t equal to infinity, this we had calculated in the last problem, if I remember correctly. Yeah, 3.75. Okay, so we know this. So we need to find Vc at 0 plus, right? And we know that since the voltage across a capacitor cannot change abruptly, so Vc 0 minus will be the same as Vc at 0 plus, right? So we just need to find the Vc at 0 minus. So how do we do that? This means that just before time t equal to 0, what is the voltage seen across the capacitor? So the circuit before t less than 0 was something like this. This was R2, and this is nothing but Vc. You see, this is the Vc, right? So so what will be the Vc at 0 minus? This is again a simple potential divider. This will be 10 into R2 over R1 plus R2, right? You can also find it using KVL. So 10 times R2 over R1 plus R2, so this will be 10 times 3 over 2 plus 3. This is K, K and K. So this will come out to be 30 divided by 5. This will come out to be 6 volts. So we have found Vc at 0 minus is 6 volts. Now we'll just put in the values over here. So when Vc 0 plus is 6 volts, so I'll write 6. So expression, so it will come out to be 6 equal to a e to the power 0 by tau plus b. So this will give me e to the power 0 is nothing but 1. So a plus b is 6. This is my first expression. Now I'll use that time t equal to infinity expression. This will come out to be 3.75 equal to a e to the power minus infinity by tau plus b. We know that tau is a positive and finite quantity, so e to the power minus infinity, this term will vanish. This will give me b equal to 3.75 volts. V is 3.75, so this gives me a as 2.25 volts. So my expression for Vc as a function of time is coming out to be 2.25 e to the power minus t by tau plus 3.75. Now we are interested in finding at t equal to 8 milliseconds, so we'll simply put t equal to 8 over here. Sorry, it's not 8 equal to, right, vc t equal to 8 milliseconds. This will be 2.25 e to the power minus 8 over 3.75 plus 3.75. I'll use my calculator, give me a moment. So 8 over 3, sorry, exponent of minus 8 over 3.75, this value comes out to be 0.118, that is multiplied by 2.25, so this comes out to be 0.266, and then we add 3.75 in that, so the final answer comes out to be 4.02 volts. All right, sorry, 4 point, did I make any errors? Just give me a moment. So vc at t equal to infinity was 3.75. vc at 0 minus would be 10 times 3 divided by 5, so that is correct. This should be 6 volts. So if this is 6 volts, 6 equal to a plus b, a plus b equal to 6 time t equal to 0, and at time t equal to infinity only b will remain, so value of b is coming out to be 3.75. 6, this is correct. Can anybody point out the error here, if any? I'm not able to see. Do you see any error in this analysis? Okay, let's go over this again. VCs should be a e to the power minus t over tau plus b. That is correct. VC infinity, so that should be b. Why is VC 0? Correct, VC has to be 0. You're correct. I'll tell you why VC, why is this analysis wrong. So if VC was, let's say, 6 volts at time t equal, thank you for pointing it out, Kunjan, thank you. So what's happening is that why VC at 0 cannot be 6. If VC at time t equal to 0 is 6 volts, this means there will be a current flowing over here, right? And there is apparently no source for, I mean, this is an infinite power supply that is being provided to this, which is not possible. So at time t equal to so what's happening is that from t equal to minus infinity till 2 equal to 0, this capacitor is not initially it was not charged, and hence at time t equal to 0 plus also it will not be charged. So this analysis is wrong over here. So what will we have is that this is equal to 0 volts. So if we proceed with that, if that the potential over here is 0, so VC will become 0, so this will come out to be minus 3.75. so I'll do the analysis again, but just let me calculate the values. It will be e to the power minus 8 divided by 3.75. So that will be negative, so 1 minus this times 3.75. yeah, correct. Okay, so let me do the analysis again. So we are interested in finding VC at t equal to 8 milliseconds. Okay, VC at t equal to 8 milliseconds. So we know the expression looks like a e to the power minus t by tau plus p. um, so to solve this, we need VC at 0 plus and we need VC at infinity. We'll find the constant C and B, and then we'll have this expression. And we know since voltage can't change abruptly, so VC at just t less than 0 should be equal to VC at t greater than 0. This voltage has to be 0. If this voltage is non-zero, this means a finite amount of current has been flowing this for infinite amount of time, which is not possible. There cannot be infinite amount of power being drawn, power being dissipated in this resistor without being apparently connected to any voltage. So you can see there is no voltage source being connected, right? So this whatever voltage this capacitor would have had, this would have been discharged using this resistor. So at VC equal to 0 plus would be 0. So let's put, so this is 0, and we know this expression was 3.75 volts, right? So let me first do this. So 0 equal to a e to the power 0 plus b, so a plus b will come out to be 0. And then secondly, at time t equal to infinity, it would be 3.75 equal to a to the power minus infinity plus b. This term vanishes, so b comes out to be 3.75. This implies a comes out to be minus 3.75 volts, and thus VC as a function of time, VC as a function of time now will come out to be 3.75 1 minus e to the power minus t by tau. Now if we are interested in at t equal to 8 milliseconds, this will be 3.75 1 minus e to the power minus 8 over 3.75. Time constant is also 3.75 milliseconds. So I calculated it just now. It's coming out to be 3.30 volts. So which was one of the options somewhere, yeah, over here. So option C is the correct one. All right. So we are almost halfway there. Right, now let's now come to question number 8. Now we are required to find I2 at t equal to 6 milliseconds. Again, this is the formulation here will be very simple. Since we know VC now, right? So I'll again do that. So remember that in the last set of questions we had also done it through two approaches, approach 1 and approach 2. I would have used approach 1 here, but since the doubt was asked there itself, so for this problem, so approach 1 is nothing but we use the Ohm's law or the KVL, however you want to put it, right? So effectively, let me write it more clearly. So approach 1 is nothing but nodal analysis. At given time. And approach 2 is, again you can say nodal analysis, KCL, KVL, whatever name you want to give it, nodal analysis for general time. So if you want to evaluate the expression for any current, let's say I2, then you go for approach 2. If the question asks, then approach 1 will not help at all. That's why approach 2 is a more general approach. If you find for a general time t, you can always input the value of the given time and you will get the answer. So in that aspect, approach 2 is better. Let's do approach 2 itself. So approach 2, I'm using approach 2. So we are requested in finding I2, right? So I2 can be simply written as, how should I do? I should say Ohm's law across R2. Very simple. So this will be, Ohm's law will say the voltage drop across R2, which is VC minus 0, treat this as a reference, VC minus 0 is equal to IR. This should be equal to I2 times R2. So I2 will simply come out to be VC over R2, and this is a function of time, so this will come out to be VC over R2 as a function of time. and we are required to find at t equal to 6 milliseconds. So we already know the expression for Vc. It looks something like this. The value of R2 is 3k, so let's put this here. This comes out to be 1.25 milli 1 minus e to the power minus t over tau. Let's take milli outside, milliamps. The unit is milliamp for current, right? So we are required at t equal to 6. So let me put t equal to 6. So I'm doing this here. So I2 at t equal to 6 milliseconds will come out to be 1.25 1 minus e to the power 6 divided by 3.75. Let me get my calculator. This will minus 6 over 3.75. So this comes out to be 0.2. 1 minus 0.2 is 0.8 times 1.25. This comes out to be 1 milliampere. So option A. Again, this problem, so we have completed this problem. I think this is the last question. Yeah, this is the last question for this set. So again, here again the approach was in fact all the 4 questions were very similar. Time constant at Vc at t equal to infinity, and then Vc at t equal to 0. We derive the expression for Vc over here, and then finally, after getting the expression for Vc, we can also get other terms, like in this case I2, the expression for that. The key difference between this problem and this set of problem, these the 4 questions now and the 4 questions earlier, was that the topography of the circuit changed. So the time constant before and after one in the previous problem were the same. Here they will not be the same, because the question the circuit topography has changed. So this is the important thing that you need to take into account, and rest analysis will remain the same, because the fundamental concepts that we have discussed, the physics that the voltage cannot change abruptly across the capacitor, will again remain the same just as before. That completes this set. So I'll again pause a bit over here, and if you have any comments or doubts till now, please ask, and then we'll take a bit of a breather, and we'll start soon right after this. So any doubts, any comments, any questions? All right, so let's now proceed for the next set of problems. So just let me check how many problems there are. 1 2 3 4 5 6 7 problems there. Okay, we have time. I think we should be able to complete easily. Okay. All right. Yeah, so this is the excuse me. Okay, so this is the problem that you can see on your screen. So for the last set of problems, this is the problem statement. So the question says, be careful now in following the question. The switch in the figure has been in position 1. This means like this, connecting A and B for a long time. So for a long time means, so what I'll do is I'll draw with respect to time, right? So I'll draw the corresponding switch positions. So this is switch, right? It is been connected in it is connecting, it is in position 1, right? So let's say it is in position 1 for a long time. So this is position 1, right? And at t equal to 0, it changes to position 2. So it changes to position 2. We'll draw the circuit, but I'm just saying. So from here, so from, let's say, rather than connecting A and B, it will now connect A and C. From here it will connect like this. Okay, and then at time t equal to 0.3 milliseconds, switch comes back to position 1. So again, so this is again position, it will again come to position 1. This is at 0.3 milliseconds, right? So the problem statement asks is that firstly, what is the time constant for this circuit for 0 greater than 0 less than t less than 0.3 milliseconds. This means over in this period, this means when the switch is in configuration 2, that means it's connecting A and C. We require to find the time constant for that particular case. Okay, so yeah, so let's go ahead and do that. So this was the circuit. Now this is we are required to consider only this. So I'll redraw the circuit. This is 5 amps. This will behave like a short circuit. This will be R2. This will be your inductor L, and this will be nothing but R3. R1 will be out of the picture. Why? Because there's no current flowing over here, right? And now we required similar. If we again the concept remains the same. If you want to find the time constant is nothing but RTH times C. That is, this is in the case of a capacitor. Can anybody tell me what's the time constant in case of a inductor, not conductor? Time constant when we are in an RL circuit. So this is what we denote as tau RC. What is tau RL? Somebody, I think, yeah, Anupama, go ahead.
R upon L.
R upon L, right. This is for inductor. So I still have problems in identifying which is which. So I only remember tau equal to RC, and I know L and C are inverted of each other. How do I know that? Because if I remember j omega L and 1 upon j omega C, these are the ZL and ZC, right? So I know L and C behave like inversion of each other. So that's a trick to remember. It's just a pointer, right? So tau RL will be RTH by L. We already know L. If you find the Thevenin equivalent for this circuit, then we are good. So how to find the Thevenin equivalent for any circuit? It's straightforward. Kill all the independent sources. So this is an independent current source, so this will become open circuited. So this will become like this. This will become like this. Sorry, it's going on. Wait. Yeah. And this is what we have is L, right? And here is what we find the equivalent resistance. So if R2 gets open, then you can clearly see RTH. Let me draw it again one more time. This is R3, and this is the L that we have applied. So you can clearly see that RTH will be nothing but equal to R3, which happens to be 5 ohms. So RTH comes out to be 5 ohms, and then tau RL will come out to be 5 ohms divided by L. L is 1 millihenry. So this will come out to be 0.2 millis. No, wait. Just give me a second. It should be R by L. No, I think it's L by R. Just give me a moment. Just give me a moment. This is RC. Time constant is RC, and omega L should be are you sure it's not L by R? Can anyone confirm it's RTH by L, not L by RTH? Okay, let me confirm. That's why I always have confusion in for time constants. I only happen to remember only for the the capacitor circuit, but not for inductor circuit. And usually I derive it using using this only. It is L by R, yeah. It is L by R, not R by L. It is L by R. Yeah, so that's why I was coming to that. So this is 1 upon omega c this. So this is also z and this is also z, right? So I was going to the multiplication should give z square. That's the trick to remember. The multiplication should give z square. So LC should be equal to R square dimensions. So if it is, let's say, so you multiply by R over here, and then you can rearrange. So that's why RC should be equal to L over R, right? So this will come out to be so tau RL will come out to be 1 millihenry over 5 ohms. This will come out to be 0.2 milliseconds. It just happens to be option A, right? So that completes the, so you can clearly see for all the problems that we are doing, the first thing always remains the same. The tau, we were first required, we are first mostly interested in finding what is the time constant, right? So now the second part of the problem asks what is I3 at 0 plus. Okay, I3 at 0 plus, where is I3? Okay, so this is I3. So we are required to find what is the current flowing through this arm at 0 plus. Okay, let's do that. So I3 at 0 plus, this is what we are required to find. Now just like in the case of capacitor, we had discussed that that we saw that voltage can't change suddenly, right? Similarly, this is for capacitor case. In this case, current can't change suddenly for inductor. Why is that? Someone pointed out the expression for voltage, right? It's L di by dt. Okay, if I is changing very fast, right, there will be a huge amount of voltage that can be generated, and thus huge amount of current can flow through these the shunt resistors that we have around that, which is not possible. Okay, so and hence the current cannot change abruptly. So please remember, so this is the concept, that this is the takeaway that we want from here, right? Right, so in other words, I should the other way of saying is that, so this is when there is a sudden change, right? So this is the first concept. Second concept, the alternatively, after a long time, current should become zero in inductor. Sorry, voltage should become zero in inductor, current will become constant, right? So because if that's not happening, if that is not happening, what that would entail is that, so if the current is changing, let's say, right, if the current keeps on changing, and I should write this, current is constant, current becomes constant after a long time. If the current becomes constant, the voltage becomes zero. So for the case of capacitor, so this is again for an inductor, this is again for an inductor. For capacitor, we saw that after a long time, current became zero. Remember, the capacitor became open circuit and voltage is constant, and voltage is constant. So this is because there the expression that's controlling is I equal to C dV over dt, right? So because you can see the positions for I and V have swapped, so that's why the nature also will swap. So here voltage equal to zero in an inductor after a long time, okay, and current will be constant naturally. Okay, so now what we are required to find here is that what is the value of I3 at 0 plus. Okay, so in order to do that, so we must see to that, we must ensure that current cannot change suddenly in an inductor. This means through this leg, so we need to identify what was IL at 0 plus, which should be equal to IL at 0 minus. So whatever the inductor current was at just before time t equal to 0, right? So before, this means just before that the switch was in this configuration, right? So we need to identify that what is the current that was flowing through IL, right? And that will give our answer, right? So you can clearly see that just before t equal to 0, so this circuit, the right half of a circuit, I'll draw only this part of the circuit now. R3, L and R3, right? So you can clearly see that no current can flow in this direction for time t, less than 0. For time t, this part is useless. So if at all any current was there, right, this would have been flowing through like this, right, in this, provided this had some initial energy stored inside it. But at time t equal to but if this circuit is on, from t equal to minus infinity to t equal to 0, all energy would have been lost. What this would mean is that there would be no current flowing, because if you remember, the energy expression is half Li square in an inductor. This means that IL at 0 minus should be equal to 0. This means no current would have been flowing, 0 amps. So this would also imply then IL at 0 plus will be equal to 0 amps. So no current would be flowing inside this inductor even at just after the switch goes from this configuration to this configuration. Okay, yeah, so that's the case. Now I'll draw the circuit. Now let me use a different slide now. Just a second. Sorry. Okay, so we saw that IL at 0 plus would be equal to 0. Now I'll draw this circuit because we are interested in finding I3 at 0 plus. What is this current, right? So I'll draw this circuit just at 0 plus. So the circuit will look something like this. This will be 5 milliamps. So now this means at 0 plus means A and C are connected. So this will be like this: R2, R3, and this will become open circuited. So but I'm still drawing this, right? And then I'll eliminate. This is L. This is how the circuit will look like. This is at t greater than 0, just t greater than or I should say t equal to 0 plus, or better, right? So this is open, so I'll eliminate this. So now the circuit will look something like this: 5 amps. This is R2, L, R3. This is the current I3 and this is the current IL, right? Now let's apply KCL at this node. I'm calling this node node A. So if I apply KCL at node A, so all the incoming current, this means this, note that 5 milliamps is coming this way, so this will be 5 amps. This should be equal to, there are two outgoing currents, IL and I3, IL plus I3, and we know that this I'm writing at t equal to 0 plus, so this will be equal to 5 equal to IL 0 plus plus I3 0 plus. This will be 0 equal to IL 0 plus is 0, we saw that, plus I3 0 plus. So this will give me I3 at 0 plus should be equal to 5 amps. To put it in simple words is that this means whatever current that is being provided by this current source, all of the current will be flowing through this resistor and no current will flow through the inductor, right? And so just let's see, yeah, there's an option D. So option D is the correct one, which directly matches our result that we have. Okay, just to reiterate this problem, because this is for the first time that we are talking about inductors and when the switching is happening. So this is the most important concept. The current cannot change suddenly whenever any switching or some step voltage, some step current is coming. So this is the only important thing that you need to consider. And the second important thing that we talk about, since we are talking about, for instance, the circuit was in operation from t equal to minus infinity to t equal to 0, and when the switch was in A and B position. So what this means is that since if an inductor is operation for a long time, provided there is no oscillations, the voltage will be equal to 0 across an inductor, and the current would be constant. So this is the important thing that you need to take into account. And the corresponding for capacitor, which we have already seen in the last problems, was that the current is 0. This means it behaves like an open circuit if it's operational for a long time, and the voltage is a constant one, right, for a capacitor. And since by utilizing this information that current can't change suddenly, we identified that IL0 minus would have been 0 amps, because if there was any if there was any current I, this means then there'll be a joule energy loss through this resistor, and which doesn't make sense, because then this would have been an infinite repository of energy, which is not possible. So this would ensure that since operating for a long time, all the energy would have been lost, and thus the current flowing through this circuit, the LR3 circuit, would have been 0. Okay, and using that information, I just redrew the circuit by putting the switch to position 2, and we draw the circuit, and then finally apply KCL to arrive at the value of I3 at time t equal to 0 plus, which was 5 amps. Okay, so now the next problem asks is that in this what is I3 at T1 minus. Okay, so what is T1 minus? Remember that so this switch was closed. If we go back, where was it? Yeah, so this is T1 equal to 0.3 milliseconds. This means when the switch goes back to configuration 1. So we're required to find what is the current flowing through this branch I3 just before that. So what is happening just before that? So we are interested in finding that, right? So I'll write this over here, that I3 of T1 minus is equal to what? And before we forget, this is 0.3 milliseconds, and if you remember, tau was, what was tau? 0.2 milliseconds. Okay, right. So what I'll do is that first I'll draw the circuit. I'm calling this as IS, which is 5 milliamps. I'm drawing the configuration when the switch is in position 2, right? So this means because I'm interested in finding what's happening at t equal to T1 minus, so I'm interested in this is the circuit diagram for this time. This is how the circuit will look like. So this will be L, and this will be your R3, right? So and this is the current that is flowing through here, I3, and this is the current that is flowing through here, that is IL, right? Okay, and again let's call this node A. Okay, so we are interested in finding I3. Then again here also, just like we had talked in the previous set of problems, we had talked about two approaches, right? Approach 1, which is the for specific time, for a given time, I should say, for given time, and then there was the second approach, which is for a general time, right? So I'll again focus on the general time, because you can always find out the particular for a particular time, you can always find out by just putting the value of t in the expression for approach 2. Okay, so as usual, let's apply first KCL at so I'll do this here. So KCL at node A, right? So this will give me is, which is the incoming current over here. This should be equal to IL plus I3. So this will give me I3 equal to IS minus IL. Now IS is a constant which is given 5 amps. IL is something we don't know. So if you somehow find out IL, that will solve our problem over here, right? So just like in the case of capacitor, we saw that the expressions could be written in the form that V equal to A e to the power minus t by tau plus B. This is for capacitor. Similarly, for the case of inductor, same format of expressions can be used. So these are the counterpart expressions. For first is for capacitor, second is for inductor. So I'll do the same thing. So I'll write simply IL as a function of time. This is equal to A e to the power minus t by tau plus B. Okay, so again there are two variables, so we must find out, we must put the boundary conditions. So that the two boundary conditions that we want to put is that what is IL at 0 plus. We estimated that IL and 0 plus in the previous problem, if you remember, was at 0 amps. The reason was that infinite energy could not be provided. Infinite energy could not be provided by this inductor, and hence it will be 0 amps. What is at IL at time t equal to infinity, right? So if you recall, we had talked about it. So yeah, so here it is. So after long time, voltage equal to 0 across an inductor, right? So we'll use this knowledge over here in this expression, in this problem. Sorry, just give me a second. Anupama, do you have a doubt? You have your hand raised, or is that from earlier? Okay, if you have doubt, you can speak. Okay, so we know that for time t equal to infinity, when t tends to infinity, inductor is equivalent to a short circuit, right? So let's just draw how will this circuit look like when t tends to infinity. Note that although we are stopping at t equal to t1, but this expression is valid for this time, but a and b, the constants a and b, are determined as if this is running for time t equal to infinity. So this can be used. So this is IS, this will be R2, right? I told you this behave like a short circuit, and this will be R3. Now if there's a low resistance path available, so all the current will be flowing through this, right? So this is nothing but IL, this was I3. So I3 will come out to be 0, in fact, at I3 at infinity, right? And IL will come out to be simply at infinity will come out to be 5 amps, right? So I'm writing this over here as 5 amps. So if we put these values over here, right? So what I'll try to do, let me copy this. Yeah, so we had I3 was 5 minus IL, and IL we saw A e to the power minus t by tau plus B, where IL0 was 0 and IL infinity was 5. So let's put these values here. So at t equal to 0, this will be A times 1 plus B. So this will give me A plus B equal to 0. This is expression 1. For second expression, I'll put t equal to infinity. This will give me 5 A e to the power minus infinity plus B. This term will vanish, so B will come equal to 5. This implies A is minus 5, and thus the expression for IL will come out to be 1 minus e to the power minus t by tau. Let's put this expression over here. So I3 will now simply come out to be 5 e to the power minus t by tau, because 5 and 5 will get cancelled and minus minus will become plus. So this is the expression that I am getting. and I'm interested in finding what time we are interested in, 0.3, right? So 0.3, yeah, t1 equal to 0.3 and t equal to 0.2. So we are interested in I3 at just t1 minus. So I'll put 5 e to the power minus 0.3 millisecond over 0.2 milliseconds. This is 5 e raised to the power minus 1.5. Let me see what it comes out to be. So the answer is coming out to be 1.115 amps or milliamps amps. So rounded off to 1.12 amps, which is your expression C. So there's one more thing, there's one more interesting thing that's happening over here, which I should point out. So you see I3 was coming out to be 5 e to the power minus t by tau, and IL was 5 1 minus e to the power minus t by tau. So these were the I will share I'll upload this session again on my YouTube channel. So let me copy paste my email ID and YouTube channel name. So these are the details. I had uploaded the previous session on the YouTube also. So if you have missed it or you want to revisit some concepts, you feel free to do so. Yeah, so coming back, so I3 was 5 e to the power minus t by tau, and IL was 5 1 minus e to the power minus t by tau, right? So let's just do one thing. Let's just try to plot them. So this is time t, right? So what I'll do, I'll plot I3 in purple. So if you see t equal to 0, it's 5. So I3 will look something like this, exponentially decaying. I3, okay, and let's put with this IL is 5. So originally it's 0, right? And so just hold on. So this is I, and this value is 5 amps. Okay, so now if I plot IL, right, IL is 0 initially, and finally it saturates at 5 amps. So this is how this is IL, right? So IL plus I3 should naturally be 5 because this is the constant voltage source, constant current source. So that's what we are seeing here. This branch is anyways not there, so you can clearly see. So sometimes I mean, not just mathematical, it's not mathematical expressions, yes, can give you the answers, but sometimes it's better if you draw the waveform. This gives you a complete picture that how are these two interacting. So for instance, the question may ask, is IL monotonically increasing? Is I3 monotonically increasing? Which of them is monotonically increasing? Which of them is monotonically decreasing? What is their summation, right? So different kinds of questions can be asked. So not just from a exam point of view, but just for an understanding point of view, this gives you a comprehensive picture when you draw the waveforms. It's a good practice if you can just draw the waveforms. That gives you an idea. Right, so I'll summarize this problem. We are required to find the value of I3 at time t1 minus. So I'll also mark t1 minus in this. So t1 minus is somewhere here, right? This is time t equal to 0, and this is time t1 minus. And before this time, so this was something like this. So this was 0. Sorry for the bad drawing, right? So this was 0 before, both of the currents were 0 before time t equal to 0, right? So this was like this, and if you see the green curve we also noticed was 0, right? So both of them were 0, but I3 had a sharp jump. IL cannot sharply change because then you will violate many principles. All right, so let's now quickly move forward to next problem. We have 4 more remaining. Okay, we should be fine. In the circuit of Q9, what is I3 T1 plus? Okay, so now if you remember, T1 plus was the time. This means when the switch has come back to position 1, right? So we are required to find I3 in that case. So we are required to find I3 T1 plus equal to what? This is what we are required to find, right? Yes. Okay. So I3 at T1 plus. So what we are required to do, again, we'll use the same principle that current across inductor can't change suddenly. Right? So what would this mean is that whatever IL was at T1 minus, this means while we are still, switch was still in position 2, this should be the same as like this, right? This should be the same. So we'll try to evaluate IL at T1 minus, and we know that. So IL at T1 plus, which is equal to IL at T1 minus, which is equal to, which was given by the expression, if you remember, we had that 1 minus e to the power minus t by tau. So what I'll simply put is that I'll put the value of t to be T1, which is 0.3, and this was 0.2. Sorry, a negative sign over here. So if we, what was the answer last time? So it was 1.12. So if we deduct 5 from 1.12, 5 minus 1.12, this will come out to be 3.88 amps. Okay, so IL at T1 plus, right, will come out to be 3.88 ampere. So we have obtained that much, right? So now what we'll do, now I'll draw this circuit at, so how will this circuit look like at t greater than T1? 5 amps. Switch will again come back to AB position, right? This is R1 and this will be R2. This will be like this, and R3. This is R3, this is L. So the current flowing here is nothing but IL. Current flowing here is nothing but I3. So no current can flow here. You can clearly see this is a resistor. No current can flow over here. And this is the circuit that we have drawn for t greater than T1. This is how the circuit will look like, right? So now you can clearly see, if I apply, let's say, KCL at this node, this was on node A, right? So let's apply KCL at node A. So I can simply write the incoming current should be equal to outgoing current. The incoming current, there can be no current coming from here because it's open circuit. It will be 0. This should be equal to IL plus I3. This will give me I3 equal to minus of IL, right? And since we are interested in finding the current at just T1 plus, so I will put t equal to T1 plus. So I3 at T1 plus should be equal to minus IL at T1 plus. So we have already obtained minus IL at T1 plus, which is 3.88. So this expression will evaluate to be minus 3.88 ampere. So this is the expression. So this is the value that we have obtained. So what this means is that, so I'll again complete that waveform that we had drawn earlier, right? So remember that this is what we were expecting. This will go if the switch had not changed at T1, this would have been the waveform, but that's not the complete picture. That's not what's happening. The switch actually changed at t equal to T1, and we noticed that what actually happened was the current became negative 3.88. So current sharply dropped to here, right? And this, and if I draw this completely like this, so this value is minus 3.88, right? So this is what's happening. So this is right. So this is what would have happened, but this actually did not happen. The current jumped sharply to this point, and IL obviously will remain to a certain degree. It will not change much. So IL, if you see, will remain at 1.12. At 3.88 amps itself. So this value here is 3.88, and hence the total current will be, outgoing current would be 0, which we saw in the KCL at node A. When we applied, we saw that there's no current can be flowing. The left half and right half are no more interacting with each other. That's the point. Okay, so for this part, now it is being asked that what is the time constant for time t greater than T1. Okay, so this is again a very straightforward problem. So we are interested in find t tau RL at t greater than t1. So I'll simply redraw the circuit for t greater than t1. It will look something like this: 5 amps, R1, R2, L, and R3. So we are interested in finding the time constant. This means we need to find the Thevenin equivalent across this inductor R. Inductor L. How to do that? We deactivate all the independent. Sir, I3 resistor. Just give me a moment. I3 resistor. Why current not linear? Current is linear. Okay, let me. That's a good point that you raised. So for a resistor, we know that V equal to IR. In this expression, I am just plotting I versus T. If I plot a voltage versus T, it will also follow this kind of a behavior, right? If I plot voltage versus T for a V3 versus T, let's say if I plot V3 versus T, it will also follow this behavior. It will be 0, then it will jump, then it will decay, and then it will jump to the negative. So it's not like the resistor is creating some problems. It's these changes are happening due to the fact that usually when we change switches, you expect the current to flow immediately, but these inductance when coupled with resistances, they induce a delay, right? So effectively what would happen is that this would have gone to 0, but that has not happened. This, rather than immediately going to 0, it's slowly decaying. So inductors when coupled with resistors or resistors capacitors together, they induce a delay. So that's why these are called transient. This means they're taking some time to reach their optimal stage. For instance, if we would have allowed it to for, let's say, 5 tau, where tau is the time constant, tau was 0.2. So if we allow the circuit to behave like if we leave it for 1 second, it will reach its steady state, and so this means there's a delay of that much time. So it's not like resistor has lost its capacity to behave like a linear device, V equal to IR. It's just that due to this peculiar property of inductor, where it forces the circuit in which it's a part of to behave it according to its wishes. That's why we are seeing this behavior. But a V equal to IR is true for this. It's just that voltage is also changing accordingly. Okay, so that property is not lost. Let's quickly derive the time constant over here now. Again, deactivate all the independent sources. So we deactivate 5 amps, right? So the circuit now, this means this will become open circuit. So circuit will look something like this: R1, this is R2, mind you these are not connected, right? And then this is R3. So if you clearly see, there cannot be R1 and R2 because there can be no current flowing through these branches. So these are of no use to us. So and this is the, so again I redraw this. So this is R3, and this is this is the L that we have. I've just redrawn this. So this is point A and B. Again, this is the point A and B. So across A and B, we are interested in finding out, right? And yes, so if I want to draw completely, so there is something like R2 which is hanging, by the way, and then here also from B there is one R1 hanging. But since these are hanging, these cannot play a role, right? So these are not considered in our analysis. So a circuit will simply reduce to R3 and L. This is point A, this is point B, and again you see RTH is coming out to be R3, which is coming out to be 5 ohms, and we know that tau RL, right, is L over R. So L is 1 millihenry over 5 ohms. This will come out to be 0.2 milliseconds. Coincidentally, this time constant comes out to be the same, as before. That means we calculate the time constant for 0 less than t less than t1. This was also 0.2, and t greater than t1 is also 0.2 milliseconds. So we have calculated that. Now the question asks in this I3 at t equal to 0.4 milliseconds. So remember that t1 was 0.3 milliseconds, right? So we are now talking t greater than t1, right? So let's do that. So we are interested in what is I3. Okay, so I3 at t equal to 0.4 milliseconds. So this means we need to draw the circuit diagram for t greater than t1. So I'll draw it 5 amps R1 L R2 R3. Again, no current can flow through this because this is open circuit, and this left half of the circuit is irrelevant because no current can come out of it. If you apply KCL over here, all the current that is coming through here has to flow in this loop itself. So what I'll try to do, I'll just drop the left half of the circuit, and I only draw the part of the circuit which is of use to us, R3 and mind you the current will be flowing here. So for instance, this R1 will have 5 amps current flowing through this, but that's not playing any role in this part, right? That's what I meant to say. Okay, so the current here would be I3, right? And the current here would be IL, and as we saw last time, right, I3 will be nothing but minus IL, right? So if you find IL in terms of IL as a function of time, then we can find I3. So now again I can write IL as a function of time as a e to the power minus t by tau plus b. We'll have to hurry a bit. So and we know that at time t tends to at time t equal to t1, that is when all the things just started, right? Let's the case when time t equal to infinity. When time t equal to infinity, so everything would have been achieved in the steady state, right? And I told you at time t equal to infinity, inductor behaves like a short circuit. Inductor is short circuit, right? So this means the circuit will become something like this. So there will be no current flowing. This means I3 will come out to be 0, or you can say, or this implies IL will also come out to be 0. So at time t equal to infinity, IL would be 0, right? And okay, and and at time t equal to t1, right, we calculated that I1t plus. In some previous problem we did do that. Let me figure it out. Yeah, 3.88. So this is 3.88. So let's put these values here. So at time t equal to t1, right? So at first let's put t equal to infinity. So t equal to infinity, this first term vanishes. So it will be 0 equal to a e to the power minus infinity plus b, right? A to the minus infinity plus b, this term vanishes. So this will give me b equal to 0, right? And only the first term will remain, and then that I can write is at IL at t1 plus this should be equal to a e to the power minus t1 by tau, right? So this is 3.88. This is a minus t1 by tau. I have to calculate minus t1 by tau again. Just give me a second. Exponent of minus 0.3 by 0.2, 0.2 to 3. Yeah, so this will give me a equal to 3.88 divided by this value. This is 17.38. Units will be amperes because everything is in amperes, right? And we are interested in finding, so I've got the expression for I3 equal to minus IL times t. So I'll put this here. I3 is equal to minus 17.38, right? That would be e to the power minus t over tau. So it'll be minus 17.38. Tau is 0.4 and tau is 0.2 and t is 0.4. So that's what we need to find now. So it will be e to the power minus 0.4 divided by 0.3. This will be e to the power minus 0.4 by 0.2. Sorry, tau is 0.2 by 0.2. So will come out to be this, and this if you multiply it by 17.38, so this is coming out to be minus 2.352 amperes. So I3 is coming out to be minus 2.352 amperes. Option B. Yeah. So again I'll just we know the note the form is again decaying e to the power minus t by tau, and it eventually saturate to minus 17.38. So if I complete this picture over here, right, so it will again continue to decay like this, and this will saturate at minus 17.38. And if I draw the green line, so green line will look something like this. This will not behave like this because switch position has changed. So what it will behave like, it will behave it will keep on increasing, and it will eventually it will go to zero. It should go to zero because we saw that so it will come something like this to zero, like this. It will decay. So that's how it will look like. Okay. No, sorry, I made a mistake. Just give me a second. So it's coming out to be minus t by tau format. So it will come and it will go to zero like this. Similarly, the other thing is just the mirror image of that, right? So it will go from minus 3.88 to 0. It will go something like this. So ignore the dashed lines, and this is how the nature will look like. We have completed the problem 14 now. Yeah, correct. So now this is what I was talking about, that infinite amount of energy cannot be given. So whenever we are approaching t equal to infinity, right, so the values will definitely saturate, otherwise there will be infinite energy. So this is the illustration for this, right? In the circuit of Q9, what is the energy lost by the inductor from t equal to 0.3 millisecond to t equal to 0.4 millisecond? Okay, so this means we are interested in finding, so during this units per millisecond, what is the energy lost? So it's simple to do. So we know that energy of an inductor is equal to half Li square, where I is the current through the inductor. So I'll simply say delta E. Let's call this delta E. So delta E would be energy of inductor at t equal to 0.4 milliseconds minus energy of inductor at t equal to 0.3 milliseconds, right? And so half of L, right, that's it will be I square 0.4 minus I square 0.3, half L. So that comes out to be common. So half of L will become common. So it will be IL at 0.4 squared minus IL at 0.3 squared. Very simple expression. And how do we know the value of IL? We have already calculated the value of IL. It was here like this, right? 17.38 e to the power minus t by tau. So IL was 17.38 e to the power minus t by tau. So I'll simply do IL at 0.4 would be 17.38 e to the power minus 0.4. Time constant is 0.2. So this will come out to be 17.38 times exponent of minus 0.4 by 0.2. This is coming out to be 2.35, which we just saw as the answer, right? And IL at 0.3, we had calculated this if I remember, but let's do it using this formula. Minus 0.3 by 0.2. So this is coming out if I replace it by 0.3, so coming out to be 3.88. We also saw this value earlier, 3.88. So I'll simply put these values here into 1 millihenry times IL times 0.4. So that's 2.35 squared minus 3.88 squared, right? So that would come out to be minus 2.35 squared. So this expression is coming out to be 0.5 milli times minus 9.53. Why minus? Because the energy is being lost, so that is denoted by this negative sign. Note, I have done energy at minus 0.4 minus energy at 0.3. Negative denotes energy is being lost, right? So if I multiply it by 0.5, so this is coming out to be minus 4.77, sorry, millijoules. So minus 4.77 millijoules. Answer should be D actually. Or did I make some mistake? I don't think so. Okay, there's one more component actually, huh? So there are two components that's happening. So all the energy that is being lost through this. No, but no, this is correct. I think D should be the correct answer if I'm not mistaken. D should be. If there are any changes, I'll correct in the next class. But approach wise, this is the problem. But I'm fairly confident 4.77 should be correct. Right. So this is how we did it. So the way we did is that. So we simply found the energy loss should be the change, whatever the energy is presently in the inductor at, let's say, 0.4 and at 0.3. We deduct those two, and we simply how to do that? We found the value of, we already know the expression for current, so we put in that, and then we simply solved it and we got the answer. Yeah, so that is it for today's class. We are just on time. Thank you for your patience, for listening. If you have okay, if you have any doubts or comments, I'll stay back, or like this specific concern that whether I can take in YouTube live. I'll try, because I have not done that. I cannot promise right now, because NPTEL usually had asked us to use Zoom and other things. But if this is a concern, that I'll talk to the to NPTEL, and hopefully we'll let you know before next session. Okay. No, there's one difference, because okay, I don't know. I'm sorry, I could not attend that Patil sir's live YouTube thing. But there's one difference also, because the number of people usually joining for Patil sir's class is usually large. So I don't know whether that is a concern, but I'll see what I can do. I can let you know. I can drop an email to you if you can share, or drop an email to me. Okay, if whatever happens, I'll let you know before the next session. Secondly is that anyways this will be uploaded to the YouTube channel. So I can understand, not you can you not everyone can join every time or stay for 2 hours. So just try to go back if you can join in the live class due to the data issues of Google Meet. Email ID I had, I'll write again. Can you see? It went now. Yeah, so that's that. I'll also share the channel link for the people who are still here. Just give me a second. Yeah, thank you everyone for your time. I'll stay back for a few more minutes. If you have any doubts regarding today's class, last class, or any specific thing that in the lecture is being talked about, feel free to ask. If in fact you can ask even in the start. That's why I usually prefer doing this in the start of the class, because at the last I myself get a little bit exhausted, and so do the other people. But if you still have some doubts, please feel free to ask. No, if not, we'll close the session. All right, it doesn't look like Anaga, Subir, and Indu. Thank you for your time, for staying late. Good night. I am closing the session now. Thank you for your time.